Welcome. In this video, we are going to jump into section 2.11 talking about related rates. We've already talked about implicit differentiation through the first few videos of this section. And so now we're going to turn the questions into a little bit more application-based with related rates. General concept of related rates is we're going to try to consider an equation with multiple variables, and we want to predict the rate of change of one of the quantities given the existence of one other rate in the problem and maybe a few other conditions. So let's go ahead and jump into the first example. We'll talk through this one together and see where we go. So example 1 says a company's revenue from selling X units of an item is given as R is equal to 1400X minus 3X squared. It says if sales are increasing at the rate of 55 units per day, how rapidly is revenue increasing in dollars per day when 100 units have been sold? So there's quite a bit of pieces of information here. So let's go ahead and see if we can break down just organizing and laying out the components of this problem. So the first thing we see is in that first sentence, we're given a couple items. We're given a couple variables and an equation. So a company's revenue from selling X items, X is one of the variables in our equation here. And this is going to be really the quantity of items that I'm selling is X. So X is going to be some production level. We're also given a revenue equation based on this X value of units. It's said that the sales are increasing at a rate of 55 units per day. So if I consider this rate for a moment, 55 units per day, I know units, number of units sold, is the X variable. So we can go over here and say that X is representing the number of units sold. And if that's the case, the rate of change of the number of units per day, this is what we're going to call our rate. And this is a rate that is going to be equal to the dx, the derivative of the x variable, with respect to time. So it's a little bit new for us, but dx dt is going to be the change in the units per our time measurement t. In this case, it's days. Time is measured in days in this question. So dx dt is the rate of change of that production, 55 units per day. So we can say dx dt is 55 units per day. And we're asked the question, how rapidly is revenue increasing in dollars per day? So revenue, how that is increasing, or the rate of change of our revenue, well, we can do that in a derivative format and say that that's going to be the derivative dr, the derivative of the revenue with respect to time. And again, we don't know this. That's what we're going to go out and solve for. But we know this is going to be measured in dollars per day. And the last component we can take into account is we want to find how the revenue is increasing in dollars per day when 100 units have been sold. In other words, we want to make sure that X is fixed at 100 units. Okay, so those are our components. We have really the rate of our quantity, dx dt, and then the rate of our revenue changing, dr dt. Those are the two rates that we want to relate, and we're going to relate them with this revenue equation. So jotting down this revenue equation, we have R is equal to, we have 1400x minus 3x squared I'm kind of leaving some space there for a reason. And that reason is we want to be able to get these dx dt and drdt terms to show up when we take our derivative of this function, because I want to relate the rates of change with this expression. So to do that, I'm going to take a derivative of both sides, and it's a specific derivative that's going to help us here. It's the derivative with respect to t. So taking this equation, I'm going to take the derivative with respect to t, that's dr dt, on the left side here. And I'll take the derivative with respect to t, ddt, of the right side of the equation. So both of these sides, we're taking equal derivatives with respect to time. So let's go ahead and work this left to right. This is going to be an implicit derivative. Derivative with respect to time of the revenue is just going to be dr dt. If we take a look at the right side of the equation, take it term by term, we'll have 1400x is going to yield a 1400. X goes away as the outer derivative with the power rule, and we want to take the derivative of that new variable x, and we would say that that's got to have a dx dt using that chain rule implicitly here. So we'd have 1400 dx dt minus 3x squared becomes 6x. And again, since we're not taking the derivative with respect to x, we have to add that chain rule piece for that implicit derivative, and that becomes dx dt attached to that. So it looks like we have the dr dt already is isolated on the left side once we have that derivative taken. And let's take a look at the components that we organized here on the right. We know what dx dt is. That's 55 units per day. And we know x, the number of units produced or being sold here, is fixed at 100. So what we can do is evaluate this expression, dr dt, at those two components. So we'll have 1400. dx dt, again, we know on the right side here is 55 units per day. Minus 6 times x, that's 100 units, and then times the 55 units per day. And when we do the evaluation for the dr dt, we should get 77,000 for that first product, minus we'll have a 33,000 for the second product, which will give us a total of $44,000. And again, this is in dollars per day for that dr dt. So dr dt, the rate of change of the revenue over time, is going to be an increase of $44,000 per day. At this moment in time, when our unit production is increasing at 55 units per day, and X is currently, or the units produced are sold is currently at 100. All right, so that is our first related rates problem. So you can kind of see the general idea here. We want to collect as much information in the problem statement as we can. We want to consider the equation with those two variables and see if we can relate, again, the two rates of change. Sometimes it's an input and output, and sometimes it's structured a little bit differently, like the next problem. But generally speaking, you want to consider taking an implicit derivative of the related equation and then evaluate it at different rates and fixed values. Let's go ahead and jump into number 2. Suppose that the price, P in dollars, and the weekly sales of X cases of pineapples satisfies the demand equation 2P cubed plus X squared equals 4,500. Determine the rate at which sales are changing at a time when 50 cases of pineapples are sold at $10 per case, and the price is falling at a rate of 50 cents per week. So let's go ahead and grab as many pieces of information as we can before we consider a derivative. So the first thing we can grab is this equation that relates the price and production level, or the sales, the weekly sales in X. So we'll just jot that down below here, 2P cubed plus X squared, and then we'll have 4,500. So we would like to go out and find the rate at which sales are changing. So sales are changing. So if I consider that variable, well, the sales is represented by the number of cases we sell. So that rate we could represent as dx dt. So that is the rate of our sales. And we're considering this rate of change at the time when 50 cases are sold. Well, the number of cases is, again, the X variable. So X is fixed at 50 cases. And we are selling those cases at $10 per case, and that would be our price. So we have a price P, which is going to be $10 per case. And again, this is the price kind of is written as a rate, but we know that is just going to be P because dP dt, this is another idea. This is the rate of change of the price. And so that would be when we try to find this dP dt, that would actually be representing how the price is changing over the weeks. So the price is falling right now at a rate of 50 cents per week. That would be our dP dt, how the price is changing over time. And we would say that would be falling, that would be negative 50 cents per week. Okay, so every week the price of pineapples is falling at 50 cents, or 50 cents less. Okay, so I think we have our pieces to consider. We want to go out and find dx dt, the rate of change of our sales. So let's go ahead and jump into the equation. We want to first, again, take that implicit derivative with respect to time. So we'll do that, d dt and d dt. We'll zoom into this, make this our focus for a moment. So let's go ahead and go through each term individually. So that first term, we have a 2p cubed. 2p cubed here is going to become a 6p squared. That's the outer derivative. And then the inner derivative for that implicit derivative would become the dP dt term. So we have an outer and inner derivative plus the second term here, we have x squared. That would become our 2x. Take the outer derivative, and then take the derivative of x itself would become the dx dt. So we have two rates there on the left that we'll have to consider. On the right side of this equation, we just have the derivative of any constant here, regardless of the variable. of differentiation we would have as 0. So the derivative of 4,500 with respect to t would just be 0. Now, at this point, we can plug in the values that we're considering, the price, the change in price, and the number of cases sold. And let's go ahead and dive into that. So we know that we'll have 6 times p squared. P is right now $10 a case. So we'll do 10 squared times dp dt. The rate of change of the price is going to be 50 cents, but it is going to be negative, so make sure we do that. So 0.05 is the dp dt. We'll have plus 2 times x, which is the number of cases sold right now. So x there is going to be just 50 cases. And then finally, we'll have the dx dt. That's the rate that we do not know. Set equal to 0. We'll continue simplifying here. We have really just 2 terms to consider. So we have 6 times 100 squared, which is, again, just 100. And then times negative 0.5. If we multiply these pieces together, we'll just get negative 300. That's going to be 1/2 of 600. And then we'll have that negative sign. Equal to 2 times 50 is 100. So we'll add to that 100 times dx dt. And then we'll try to solve here for dx dt. So adding 300 to both sides. Will get us pretty close to what we need here. 300. And dividing by 100 looks like we will come out as an even 3. Canceling those out, we'll have some zeros canceling here and dx dt here. We'll simplify down to just 3. And here, notice that this is the rate of change of sales. And so sales is measured in cases per week there. So that rate of change would be an increase of 3 cases per week. So as the price decreases over time here, the sales has to increase to keep up with the demand there. So dx dt is going to be just 3 cases per week of increase. So let's take a look at maybe one more in this video. This question says that a pebble is thrown into a pond and the water in the pond starts to ripple in a circular motion. The radius of the circular ripple is growing at a rate of 3 inches per second when the radius is 2 feet. Find the instantaneous rate of change of the area of the circular ripple with respect to time. Okay, so this has a little bit of a different flavor. It's more of a geometric shape that we would see instead of a revenue or cost or price function. So let's go ahead and draw a picture maybe to represent what's going on. We have a pebble thrown into a lake or a pond, and it creates a circular ripple. So I have a little rock thrown into a lake, and then it starts to make kind of a circular ripple that we see here. We have our kind of circular ripple, and again, this ripple is expanding in such a way that the radius here that goes out from this ripple, I'll get rid of that just to is increasing or growing at a rate of 3 inches per second. So if this is my radius, I'll call that r of this circle. We know that the rate of change of this radius is 3 inches per second. So how would we describe this? Well, the rate of change of any quantity can be represented by the derivative with respect to time here. And so we have dr dt, that's the change in the radius with respect to time, is equivalent to 3 inches per second. 3 inches per second. Again, this is the rate when the radius is currently 2 feet. So r currently is fixed at 2 feet. Now, I want to make a quick point about our units here. Notice that the rate of change is in inches per second, and the actual length of the radius of this ripple is measured in feet. That's not going to be helpful for us when we try to relate the rate of change of the area, because inches and feet are measured differently. We want to make sure that we are in the same units to be able to connect these two objects. So 2 feet, otherwise known as 24 inches, might be helpful here. There's 12 inches in each foot, so 2 times 12 is going to give us 24 inches. We're going to want to consider this as 24 inches instead of just 2 feet. If we use the value of 2, when we go to evaluate this later, we will come up short because we're not going to be in the right units. Okay, so let's go ahead and now consider, we want to find the instantaneous rate of change of the area of the circular ripple with respect to time. So now we want an equation. They don't give it to us here, but we want to find an equation that relates the area of this circle with this radius. And if I give you a moment here, you might come up with this equation. It's just going to be, how do we find the area of the circle? And you probably are saying this. This is going to be area equals pi times r squared. So pretty familiar geometric formula. Area equals pi r squared. So this gives us the area of any circle with the value of its radius. So we don't want to be too eager to plug this value of 24 inches in quite yet, because we want to be able to relate again the change in the radius over time. And again, I'd like to find dA dt. That's going to be the value I want to find, which is the instantaneous rate of change of the area with respect to time. That's what I'm after. So let's go ahead and again consider an implicit derivative. We're going to take the derivative with respect to time one more time here. ddt. Again, time in this problem is represented with seconds, so that could change from problem to problem, but we're still taking the derivative with respect to time. The derivative does not change. So the left side we can consider here as just dA dt. If I take the derivative with respect to time on the right side, we can say that pi here is going to be a constant. The r squared can become 2. I can pull that out in front if I'd like, and then r to the first. And then since we are not taking the derivative with respect to r, we're taking the derivative with respect to t, I have to do the chain rule piece, which is going to be the derivative of the r variable with respect to t. So we have dA dt equals 2 pi r dr dt. All right, and now since I'm trying to just find dA dt, I can consider evaluating this derivative expression at two different values. The radius currently is 24 inches, and the dr dt, the rate of change of the radius over time is 3 inches per second. So we can say that dA dt is equal to, we'll have 2 times pi times the radius, currently is 24 inches. We want to make sure that's in inches. And then the dr dt is 3 inches per second. Multiplying these all together should give us 144 pi. If we keep this in terms of pi, we'll have 2 times 24 times 3. Put that in a different color. So 3, 24, and 2 give us 144 times pi. Don't forget that pi. And our units here, if we take a look, are going to be inches times inches, which is inches squared per second. And this shouldn't surprise us because we're taking a look at the rate of change of the area now. And so we should have area units. In this case, it would be inches squared per second. So we'll take that as our result. That would be our exact solution in terms of pi. So hope this is a good starter video for you guys to start to understand these related rates. Look forward to seeing you in the next video, and we'll take a look at that next.